So here's our next problem. Uh, and what do we have here? So this is another carnival problem. A lot of carnival problems use Coriolis. Uh, so what do we have? So we have, this is an XY plane where this is ground and this is going up into the air. And so this would be a pivot point. So the idea is there's a motor that would take this thing AB and spin it up. Okay, so people would be in this cage here, as it were. And then I have this cage. So this is going to spin up at 2 radians per second. And meantime, the idea is in this case it's going like so. And the whole while, then the cage is rotating the opposite way. This would be one wonderful carnival ride for causing people to puke. It would really have a great effect. So, but for where we are now, we have, so picture this is a pivot, and this thing's going to go like so. So we have, this is 10 feet from A to B, currently at 30 degrees, going at 2 radians per second. And then this piece right here has a radius of 2 feet, so wouldn't be many people in it. And it's spinning the opposite way at 0.5 radians per second relative to AB, not ground. And we want to find VC and AC. And we're going to do it twice. We're going to do it once with Coriolis, and then we'll do it again with ground coordinates. Get the same answer, of course. So relative to Coriolis, here's what we have. We have A to B, 2 radians per second. And then at B, we have this other bucket thing. And it's rotating the opposite way at 0.5 radians per second relative. Okay. So that's just the picture of what we have. Now, to use Coriolis, what do we need to do? Okay, I can't go to B. I've got to go, let me put it this, I need to envision this bar AB as having a plate of metal attached to it, so that we can envision there's a spot C on link 2, and then a spot C on link 3, which is this extra bucket here that's spinning around. So I've got to go and figure out the velocity as if it was on link 2 of C, and then jump to C on 3. All right. This sometimes bothers people because they're like, well, there is no C on B. Well, just imagine you just welded a plate on, so you created a C that's on link AB. So that's what we're going to do. So we're going to go, if you look here, velocity at C is going to be velocity of C1 relative to A, so that's meant to be on this link. And then I have plus velocity of C2 relative to V1. So I'm jumping from this link to this link at point C. All right. So to do that, so to jump from here to there, I've got 2 terms that I've done. All right, and I just split them out. So we have 2z, that's what this is, counterclockwise. And then to go from A to C, I have 10 cos theta x plus 10 sine theta xy. Say that again. This is 10 feet. So I have 10 cos theta x plus 10 sine theta y to get to B, and then I'll have to subtract off 2y to get to C. That's what I have here. The 2's are both the omegas, and I've just split these apart. 10 cosine 30 degrees x plus 10 sine 30 degrees y minus 2y. That is all to give me the velocity of C on link AB. All right. Then I need to make the jump from link 2 to link 3. All right. So if I could weld a plate onto this thing, so I could lie on the plate somehow or hang on it and watch what C is doing, what would I see? Well, C is rotating relative to this piece, but the velocity at the moment is it's going that way. Omega cross R that way. So this is 0.5 radians per second relative to AB. So I have 0.5, this is clockwise, so minus 0.5z cross minus 2y. That's what this is. So here is the v relative term. All right, add them in. So just take that, multiply all this thing out, and we might wind up with minus 7x plus 17.32y. Time to move to the acceleration side. Let's move this up a bit. So, what do we have for this? The way I did it is I just broke this up. I went from B to C on this link 2. All right, so I just, rather than have basically a 10 cosine 30x and then 10 sine 30y and a minus 2y in the same term, I just distributed them. That's all it is. Now note, to figure out what is the acceleration here on the link 2, we don't have any alpha. There's no angular acceleration, so those terms are gone. All we have left is omega squared r. So omega is 2. Omega squared r takes me to B and then to C. All on link 2. At that point, we start our Coriolis stuff. So here we have all of the stuff we had from velocity. So 2 times, okay, 2z, that's this piece, link 2. And the velocity we found for C, that was up here, minus x from doing that. So those terms just pop up. And then once again, we have the question, if somebody could be sitting on this link watching what C's doing, what they're seeing is simply something on a basic circular path. It's spinning at constant angular velocity, but the circular path tells us we have normal acceleration, which is minus omega squared r. So we have minus omega squared, r is minus 2y. Plug and chug. And that takes us down to our bottom answer, which is right there. So now we're going to do this whole problem again, just conventionally. And to do that, all we have to do is convert this 0.5 from a relative into a ground angular velocity, reference to ground. Okay, let's make this happen. So, here we have the basic setup. 10 feet to get to B, down 2 feet from B to get to C, and here's this 0.5 radian per second rel. We'll just put that note in there. All right. So here's what we need to do is to convert that into rel. We have this was 2 minus 0.5, 1.5 radian per second ground. And there we are. So the difference now is that I will go from here to B, which is shared. B is on link 2, it is on link 3. So I'll go from A to B and then B to C via ground. So 2z cross 10 cosine theta x plus 10 sine theta y. That takes me to B. Now 1.5 radian per second relative to ground minus 2y. Multiply it all out, get the same answer. Acceleration. Again, the alphas disappear, but now we simply go to B, so we have minus omega squared r from A to B, and then given the ground angular velocity, minus omega squared r from B to C. And we do that, and of course we come up with the same answers all over again. And that finishes this problem. We have one more left to do, and we're out of Coriolis. Catch you soon.